Okay, we'll get started on the heteronuclear diatomic MO diagram, and then we'll pause to take a review Kahoot. All right. Good morning. So last time we went through the MO diagram for a homonuclear diatomic, right? Same atoms on both sides. Today we're going to talk about carbon monoxide and get into a heteronuclear diatomic. So again, it's pretty easy to do MO diagrams for diatomics. And then we'll start to look at polyatomic molecules at the end of this one. And don't panic when you see it, because it gets pretty complicated very quickly when you get past two atoms. Okay, and so let's dive in. All heteronuclear diatomics are C infinity V's. So if you see, CO or Cn minus or something like that, where you've got two atoms that are different, it's going to be that C infinity V point group because it doesn't have a point of inversion. The two atoms are different. And so if you have a homonuclear diatomic, it's going to be D infinity H. The C infinity V character table also, because it was one of the original ones, was they started using the Millikan notation in Greek, but now it's switched over just to A's and E's. And so here's the translation from, sigma plus is now A1, and sigma minus is A2, and so on. We got rid of the pi's, the deltas, and phi's, and we just do E1, E2, and E3. Also, I noticed, I've put on here for you the Z and Z squared orbitals. Those are going to be in the Z squared, X squared, and Y squared. That's going to represent S orbitals. And then the PZ orbital obviously is the Z. Sigma and sigma star are going to be the same on top and bottom. And so they're going to be Z squared type orbitals. And so this is a key as well to find Millikan notation for the different MOs that you have and the different atomic orbitals. So whenever you're working on bonding and making these particular MO diagrams, you need to use the character table to know the symmetries of the atomic orbitals and then also the symmetry of the molecular orbitals. So you want to write this down because we're going to use this over and over again. Only orbitals of the same symmetry mix. So only orbitals of the same symmetry can mix. So whenever we're making an MO diagram, you can't mix a px orbital with a pz orbital because they're going to be different symmetries. Okay. The px orbital and the py orbitals are going to be x and y, and those are going to be in the E1 symmetry. And then the s orbitals, the pz orbitals, those are going to be A1, and so they'll mix together, but they won't mix with px's and py's. Now we also have pi bonding. Pi bonding is going to be with the x and y in phase, and so they're going to retain that x and y character, and so the pi bonds are going to be x or y. So if you have a pi bond, it's going to either be x or y symmetry, and it's going to be E1 if it's a heteronuclear diatomic. And then if you have a pi star, you get that plus minus pattern. So you maybe can picture it in your head. We'll have pictures of them in a second. That plus minus pattern sets up an XZ or a YZ. Now it's still E1, but more specifically it has the symmetry of X times Z or Y times Z. So this is the character table for a heteronuclear diatomic, and then this is a bit of a key for understanding where the atomic orbitals lie and where the molecular orbitals will lie. Now you might ask, well, what about these others? Well, some of the ones like the E2 row takes into account some of the d orbitals, but we're really not going to get into the d orbitals. Okay, but they're on there. Now, are there any orbitals associated with E3? No, none of the ones that we deal with. So you just don't have to worry about E3. That's not going to be a symmetry of any of your MOs or any of the atomic orbitals. Anybody need clarification on this? All right, let's move on. So let's make HF, one of the simplest diatomics you can make. Just take a hydrogen atom and stick it on another atom, and you can see how the orbitals work out. And so what do we have? First of all, whenever you're making a molecular orbital diagram, you have the atoms on the left and the right. So you have the atoms on the outside, and they come together and make the molecule in the middle. Okay. And so over on the right side we have hydrogen, on the left side we have fluorine. we have the atomic orbitals for both of those. So the fluorine has the 2s, and again, the bonding only takes place with the valence orbitals, so we don't worry about the 1s on the fluorine. So just the 2s and the 2p. So we have the 2s orbital on fluorine, we have the 2p orbitals on fluorine. And they're going to bond with that valence orbital on the other atom, and in this case it's hydrogen 1s. Now you wouldn't really know the relative energies of these atomic orbitals. Okay, so how do I know that the hydrogen 1s is above the fluorine 2p's? The only way I really know that, if I had to guess, would be that the highest orbitals in both atoms are going to be close to each other, but the one with the most protons is going to be a little lower. So if you're looking at that, the fluorine has more protons than the hydrogen. It's going to pull those electrons in a little closer, so it's going to lower the energy. And so we would see that the hydrogen 1s is probably the highest energy orbital. Okay, it only has one proton. It's not pulling those electrons in very closely. And the thing that's energetically stabilizing these orbitals is that Coulombic attraction, the positive and negatives being attracted to each other. And so this is the symmetry from the character table, A1 for the s orbital on hydrogen. It's going to be A1 for the s orbital on fluorine. And the pz orbital on the fluorine is going to be A1. So we could go back to the character table and see that there's 3 A1s in these atomic orbitals. And what did I just tell you to write down? Atomic orbitals of the same symmetry can mix. And so this is how you keep track of the number of little orbitals you have in the middle. Right? How many lines do you draw in the middle? You've got a molecule. How many orbitals, how many energy states are there going to be? Well, if you mix 3 atomic orbitals, you get 3 molecular orbitals. So the number of orbitals is conserved. So I come in with 3 orbitals that mix together, I make 3 mixed orbitals. I make three molecular orbitals with 3 atomic orbitals. And so how do I draw the energies? I mean, you can kind of see through my little shaded panel, but if you couldn't see through there, just think practically. I mean, these 3 orbitals come in, you're going to have a really good bonding one, you're going to have a really bad anti-bonding one, you're going to have one in the middle. For our purposes, that's good enough. Do you follow me? So you draw a line that's a little bit below the 2s, you draw a line that's a little bit above the 1s, and then you draw one in the middle. And that's what we have here. The 2s drops a little bit because it's interacting with the 1s. Not much because they're far away, but it interacts a little bit. So again, the box for that electron in that orbital has expanded a little bit, drops the energy. Okay. And then the middle one, and then the upper one. So you have the 3 orbitals produced by mixing 3 atomic orbitals. Now you have 3 molecular orbitals. And so when I say draw one that's low, one that's high, I'm just talking about I brought in these 3 orbitals. I'm going to have one that's low here, and I'm going to have one that's high here, and I'm just going to draw one in the middle of those. You can do that. Okay. Pretty simple. Now the px and py do not have anything to mix with on the hydrogen. There's nothing in the hydrogen atom that it can interact with. So there's no E1 atomic orbital that's occupied on hydrogen. There are px and py orbitals on hydrogen theoretically, but they're way high in energy. There are no electrons in there. They're unoccupied. And so we're just talking about the orbitals that hydrogen brings in with electrons. So its valence orbital is a 1s. And there's no E1 symmetry to it. So the px and py just come over to the middle of that MO diagram as non-bonding orbitals. So those are non-bonding electrons in those p orbitals. And we can see the pictures here. So look at the pictures and then look at the molecular orbitals that we've drawn and think about, can I do that? You know, can I draw these pictures? Let's focus on the A1 orbitals first. Okay? What's the first A1 down here? It's the lowest energy one, and it has 0 nodes. Now the reason the 2s is bigger than the 1s is because it's so low in energy, it's very similar to the 2s. But basically, if you had drawn this right here, what I'm drawing with my pen, and shaded it in with no nodes, that's good. Right? the 1s and the 2s are in phase with each other. They make one molecular orbital, no nodes. That's the lowest energy one. And then we go to the middle orbital that we drew. What do you think it's going to have that the bottom one didn't? A node. So if you go up to here and you drew this orbital, now notice it's a PZ interacting with the 1s, and so the node is in that PZ. So if you drew this shape, with one node, that's good enough. Okay. So we have 0 nodes at the bottom, 1 node in the middle. What do you think the top one has? It has 2 nodes. So if you came up here, they have the PZ out of phase with the hydrogen 1s. And if you drew this, then that would be great. So those are the kinds of pictures that I would be looking for if I was grading your work on this. And then I would want to see the symmetries labeled too. How did you get those? You mixed the A1 atomic orbitals. And so all 3 of those would be A1. Okay. So when I'm talking about teaching you this, this is an MO diagram, and I would like for you to be able to pretty much produce everything you see on this diagram. The symmetries, the pictures, where the electrons are, the 2 atoms on either side, the molecule in the middle. This is an MO diagram. So I want you to be able to produce this. If I say draw the MO diagram for HF, this is your task. Start with the atoms, H and F, do the atomic orbitals, then start mixing the things that have the same symmetry, A1, 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 you have 3 in the middle. Draw your little pictures just to confirm in your mind that you know what orbitals did what. Bottom one has no nodes, top one has the most nodes. Work your way through the middle. Okay. And then the PX and PY, they don't have anything to do with the hydrogen 1s, so they just come over by themselves. You have the PX here, and you have the PY there, and you have the coordinate system. So the z-axis is the axis of the molecule, so that's why it's drawn sideways, because we typically draw these molecules sideways, and so the z-axis is going left and right. So I know it looks intimidating if you just get it thrown at you, but if you work it piece by piece, then you can do it. So what pieces trip you up? Like if you were given this assignment right now, what would trip you up?
The E1.
The E1?
Yeah, because you're saying like do lower, middle, top, but then the E1 isn't part of that?
Right, because the E1's not mixing with anything. And so when I say mixing, these orbitals bump into each other and interact. That's what I mean by mixing. And so if they don't overlap, then they don't bond or they don't antibond, they don't interact. And so the PX and PY are oscillating, I guess, this way, right? So let's pick the Y orbital. It's oscillating this way, and the hydrogen's oscillating in and out. And so you say, well, when it oscillates forward and the hydrogen expands, it's interacting on this side, but it's not interacting on that side. So every positive interaction you have is canceled by a negative interaction. So there's another way to think about it too, is that PY orbital has a node that goes right through the hydrogen. And so it kind of cuts that hydrogen orbital in half, but the hydrogen orbital is a sphere. So if you take those functions and multiply, remember that we're multiplying these wave functions and integrating over all space. And so the positive sides and the positive sides multiplied by each other produce positive numbers, which would give us a non-zero integral. But the negative side of that p orbital is multiplied by the positive side of the s orbital, and that gives us the negatives numbers. And if you integrate over all space, you get a zero interaction. So you think about these wave functions. These are functions. And when they're multiplied by each other, the positives and the negatives can cancel each other out, and you get no net interaction. Yeah?
So, but you still put the electron from the hydrogen into this?
Yeah, so then all of the electrons from the atoms are now molecular electrons, and they go over the whole molecule.
Okay.
And you start at the bottom. We brought in 7 from the fluorine and 1 from the hydrogen, so we have 8 total. And so then we just start at the bottom at 2, 2, 2, 2 until we run out.
Okay.
Yeah, and so we really don't know which hydrogen electron went where, because now it's no longer a hydrogen, it's just in the molecule. So that's a good question too. So whenever you finish with the orbitals, then you start at the bottom and just fill them up on the bottom.
Will all heteronuclear molecules have an E1 somewhere?
Yes, the pi and the pi stars will be E1s. Yes, and you can go back to that character table in the previous slide to see that. Let me back up a little bit. Here, see that E1? Those are the pi and the pi star symmetries. And those are also the PX and PY symmetries. So the PX and PY in these heteronuclear diatomics will always be E1, and they'll mix to form E1s.
And will they always be between the top and the middle?
Yeah, so we'll split those sigma bonding interactions with the, and you know, we'll do one in a second that's carbon and oxygen, so carbon monoxide. So then we have p orbitals coming together and s orbitals coming together. So we're doing HF now, but then next we'll do CO, where we'll have, it'll look a lot like the homonuclear diatomic, because we had the p orbitals across from each other and the s orbitals across from each other. Yes.
So then whenever you want to like nitrogen or something, when you actually flip the order, does that doesn't change the Millikan notation then?
We don't flip the order on these heteronuclears, so we're,
Okay, so
yeah,
that's-
yeah,
Okay.
yeah. So these are great comments. And so this sets us up. We really have, you know, I guess if you were to calculate the bond order, those electrons in the from the px and py come straight across. There's really no bonding taking place with that orbital. So that would be a non-bonding electron pair. You know, both of these in the middle. So you see these are non-bonded. This is clearly, see the electron density is covering the bond. And so that's clearly a sigma interaction. This one is mostly the two electrons from the 2s. And so in order to get the bond order to work out as a single bond, HF, we're really seeing that lowest one as a non-bonding. The middle one is the sigma bond, and the two px and py's are non-bonding. And so we have two bonding electrons, 0 antibonding electrons, and so we have a bond order of 1. So that tells us that we should expect a single bond distance in HF, not more like a double bond distance. Anything else that you need clarification on before we move on? Okay, now that let's pause with these pictures. Let's work with these pictures a little bit and take a Kahoot. These pictures are from the no internet. How about that? Huh. Well, we'll come back to that, I guess. You can put your phones back down. Yeah. Strange. Okay, so how do we know these things are located where they are? Of course, we can go to X-ray photoelectron spectroscopy. We can freeze some of the HF onto a solid surface and shoot X-rays at it and look at the UV light at the electrons and the binding energy. And we have this ionization limit, so if we shoot electrons past that ionization limit, they come off with the excess kinetic energy. We run them to an energy analyzer, and we can measure the different energies. So we know where the fluorine orbitals are, we know where the hydrogen orbitals are. We can do those separately, and then we can do the molecule where we get the that bonding arrangement and the non-bonding, and then we can actually measure if we put some electrons on there and make FH minus, then we can measure where that next orbital is. So the data supports, of course, the MO theory, the electronic structure of the molecule. So now let's look at carbon monoxide. I wanted to get specific, actually try to be as accurate as possible for this molecule. And so I ran the atomic energies and the molecular energies using density functional theory in Gaussian. And then I copied those energies from that log file to Excel and plotted them. And so I built this molecular orbital diagram. I didn't build it by hand. I built it using Gaussian. And so there's a few things in here that are finer details that I wouldn't expect you to do. But in general, it's the same exact exercise that we just did that you could do by hand. So in these output files, you see the energies of the different orbitals. The negative ones are going to be occupied, and the greater than, the positive ones are going to be unoccupied. And so here's the carbon monoxide MO diagram showing the core electrons. And so on the left is carbon, on the right is oxygen, and it's all crammed up at the top, right? So you can't see what's going on in the valence band very well, but you can see the core electrons. And so here we see oxygen's core electron on the right and carbon's on the left. And when you bring these together to the molecule, those don't change energy. They don't interact because they're held so closely to the nucleus. Now, who can tell me why oxygen's is so much lower in their 1s than carbon? Anyone? Why would oxygen's 1s orbital be so much lower than hydrogen?
More protons.
Exactly, that's it. More protons. And so this is actually how we filled out the periodic table. A guy named Moseley was looking at X-ray fluorescence, and he was looking at how you ionize an atom and then you get X-rays out. So you can look at X-ray fluorescence, you hit it with really strong X-rays, and then you get other X-rays out. And he was exciting 1s electrons and creating a hole, and then 2s electrons were dropping down and giving him a characteristic energy for every atom. And he noticed that if you went through the periodic table, that this would just march right along and tell you the identity of the atom. And what was neat was there were gaps. And he said, these are undiscovered atoms. And so we just had this data, and he said, there's this line here, we're missing one here, missing one there, missing one there. And so then they knew if they discovered a certain ore or whatever and they started extracting, they could just run X-ray fluorescence on it. And when they saw a peak in the missing area, they knew they had one of the new atoms. They just needed to isolate it and characterize it. But they knew that sample contained one of the elements that we didn't know about yet. So that's pretty cool. If you look at it and you get all the ones that you already know, it's not an interesting sample. And so then you just keep looking at the craziest ores from mines in, Croatia and all these different places, and you find these really exotic ores, and you could hit them with X-rays and see, oh, this contains the unknown atom that's right there. It was really hard to find technetium-99 because it's a metastable atom. It decays. It's radioactive right there in the middle of the periodic table. And this was how we found it. We found it through this X-ray technique. And so that's kind of an interesting thing. But yeah, that 1s electron energy is diagnostic. You can just run that through an X-ray machine and see what elements you have in your sample. If you can get the light in and out. Solid samples are opaque, so you can't always get them. So then we zoom in on the valence area, and these are all of the energy levels. It's a little bit confusing if you look at it carefully. We have the carbon atom on the left and the oxygen atom on the right. Now it looks a little different. Can you explain to me what's going on? Let's just focus on carbon. I have one orbital at the bottom. What do you think that is?
S.
An s orbital. Which s orbital?
2s.
2s. And then we have 3 up there, but they're not equal in energy. Px, Py, and Pz. And why would they not be equal in energy? Look at carbon. How many valence electrons does it have? 4. And 2 are in the 2s. So how many are in the p orbitals? 2. And are they in the same orbital or different orbitals? Different, right? They're spin up, or we just typically put them spin up first and until we get all 3 in there, and then we start pairing them up. And so what we have is the 2 occupied p orbitals are a little bit lower in energy than the third one that's unoccupied. Okay. Same thing for oxygen. We have the 2s, and then we have the 2 p's, and the 2 occupied orbitals are have got two unpaired electrons, and then the one that has two electrons in it is a little bit higher in energy, the PZ. Okay. So those are the atomic orbital diagrams. We filled them with the electrons. The 1s orbitals take up 2 electrons each as well. And so then we know the symmetries of these things. The s orbitals are colored blue, and that corresponds up here with the character table. You see the blue row is A1. And so all of the blue orbitals are going to mix, the z orbital, pz orbitals, and the 2s orbitals. And so now I'm bringing in 4 orbitals, right? I've got two 2s orbitals, and I've got two 2pz orbitals. So I'm coming in with 4 atomic orbitals that are the same symmetry. I'm going to make 4 molecular orbitals. And even though Gaussian generated this, and you don't know the exact energies of those, what are you going to get? You're going to get a lower one, so that 2s is going to drop in energy, and then the highest one, and then you're going to have 2 in the middle. So you can see those on this diagram. You see the lowest one here. So if you're drawing this yourself, you'd put one down here, and you'd put one up here, really high in energy, and then you'd put 2 in the middle. And so those are going to be all of your blue orbitals, your A1 orbitals, and they're singly degenerate. Okay. The lowest one's going to have 0 nodes, then 1 node, then 2 nodes, then 3 nodes. Okay, so that's pretty straightforward. Okay. So let's show. So these orbitals are connected there, all 4 spots. So those mix. So we're drawing those little lines. It gets busy. That's why I did it in color. Okay. So that's where those 4 orbitals came from. One that's low, one that's high, 2 in the middle. You can do that. Now the pictures are where it gets complicated. But drawing the diagram is pretty easy. Okay. You follow it? Yeah. Okay. And then notice we're not dealing with the electrons just yet. Now let's mix the E groups, the E1s, so the PXs and the PYs. So I'm going to have 2, sets of atomic orbitals come in. They're degenerate in energy. They're going to form a degenerate pair that's low and high. Okay, so they come in degenerate. They mix side by side. They form 2 low and 2 high. Now I might have, no, they look pretty evenly spaced. Notice the amount that this one drops right here. Well, no, I mean, this doesn't drop very much. I probably would have put these lower. And, if these go up that much, then typically I would make this one go down that much. So I would have drawn it a little differently, but Gaussian is giving us maybe a more accurate view of it. Okay. If you were to put these orbitals here down below this one, I mean, I couldn't say that you were wrong. Okay, I'd have to do a Gaussian calculation to prove you wrong. Okay, so if you put them below that one, that's fine. The main point is you don't mix this. You keep the symmetry straight. You go low and high, and so that's the level of detail that I'm looking for. Okay, so let's mix those. These. So those would be also the sigma, sigma star, sigma, sigma star. But we'll get to the pictures and we'll see how the sigmas and sigma stars work. And we have now the PX and PY mixing. And so we have all of our electrons in there. Everything's paired up. This is a nice singlet molecule. We didn't talk much about singlet and triplet, but it's the same kind of thing we had with the atoms. If you have unpaired electrons, the number of unpaired electrons plus 1 is your multiplicity. Okay, so each one of those is a half. You add them together and so on. So these are the number of unpaired electrons is 0 in this case. Plus 1, it's a singlet. So, okay. So are there anything you need clarification on this? We have the pi and the pi star. We have the sigma, sigma star, sigma, sigma star, just like we had in the homonuclear diatomics. Yes?
You draw the P, X, and Y below.
The sigma star.
Would it affect the electrons? Like when you're pulling out?
If we go back to the homonuclear diatomics, it was that wide table that showed all the MO diagrams for the whole second row. And it would affect when we have unpaired electrons and when we don't. So it would be one of those things we'd have to detect that by paramagnetism, or some other way where we could detect the multiplicity of the molecule. In this molecule, it wouldn't matter because both of those are fully occupied, so we wouldn't be able to tell really. We could tell from UV photoelectron spectroscopy probably by the shape and size of the peaks. So depending upon how if you're shooting X-rays at a molecule and kicking electrons out, that every orbital has kind of a different cross section. So you've got to hit it with a photon to get the electron out. And if the orbital is really huge, it may have a lower signal just because the electrons spread out. But if it's a really tightly focused orbital, then it maybe has a taller, narrower peak. So you can tell from the UV photoelectron spectroscopy kind of what type of orbital you're dealing with. But it would be tricky to find that out. Okay, so now we have this question, and this is interesting about carbon monoxide. If you're doing the Lewis dot structure, maybe, I don't know if you've ever been bothered by carbon monoxide, but it's one of those that we don't really talk too much to the freshmen about carbon monoxide because it kind of bothers you when you have the formal charge. You ever talk about formal charge where you want to reduce the number of charges on the molecule? And in this case, if you do the octet rule for carbon monoxide, then you have a separation of charges. So you have positive oxygen and negative carbon because the carbon can claim 8 electrons. It comes in with, let's see. No, here it's coming in with 4 electrons, and yet if you look at this, it can claim 1, 2, 3, 4, 5. So it can claim 5 for the formal charge as you split these covalently bonded electrons, and you take 1 to each atom. And so it's got 3 electrons in a bonding arrangement, 2 non-bonding, and so if I satisfy the octet rule, when I calculate the formal charge, it makes a negative carbon. And it makes a positive oxygen. So I don't like that. So if I want to reduce my formal charge, I go over to this one where the oxygen has a 0 formal charge. It brings in 6 electrons and it can claim 1, 2, 3, 4 and 1 for each bond. So it can claim 6 electrons. And carbon brings in 4, it can claim 4. So this has 0 formal charge on carbon and 0 formal charge on oxygen. But it doesn't have the octet rule. So we've got this conflict between the octet rule and between the formal charge way of doing the Lewis dot structures. Well, if we look at this, we might say there's dipole moments. So we have a dipole moment that goes from the oxygen towards the carbon in the formal charge, in the octet rule case, and in the formal charge case, we have a dipole moment that goes from the carbon towards the oxygen. We can actually measure this. We can actually see also from Gaussian, what does it tell us? So we go into Gaussian and it tells us that the carbon, if you look on here, the carbon is positive. So down here, the carbon is showing us that it's positive. And so if we look up here, what's the bond order? We've got 2, 4, 6, 8, back down to 6, divided by 2, it's 3. So we have a triple bond according to our bond order, which would favor the formal charge, but then we have a dipole moment that favors the bond order favors the octet rule, but the charges on the atoms favor the formal charge formalism. So that's carbon monoxide is a very strange little diatomic. It looks like it has a triple bond, okay, but the dipole moment's going in the wrong direction as to what you would expect from that triple bond. So how does it associate with molecules? Well, that double bond, or that lone pair on carbon is really, really important. And so let's look at some of the pictures. So we have down here the sigma star, the sigma and the sigma star. So these are all of the bonding interactions here. So we've taken these bottom 4 and then these ones up on top, and we've put them in here. We've got, again, no nodes in the lowest one, 1 node in the sigma star, 2 nodes in the sigma, and then 3 nodes up here in the sigma star. Can we see how these were constructed? Yes, these are S-type orbitals. The nodes are a little funky because, again, Gaussian's trying to find the minimum energy for the orbital. And so this is using a lot of the orbital on oxygen, and this is using a lot of the orbital on carbon. But you go from 0 nodes to 1 node. That node breaks the bond a little bit, so it's antibonding. Look here, we have the PZ orbitals interacting with each other. So for this one, if you were to just draw this picture where you have the PZ orbitals on these, and you shaded the ones in the middle, then I would like that picture. That would be fine. Okay. You just have the PZ orbitals coming in, and the two lobes that are touching have the same shading. And so that's a good picture. Down here, if you were to draw this one is carbon, oxygen, got the bond in the middle, and you just drew 1, 2s orbital shaded, and the other one not shaded, that's a good picture. Here, if you just drew this picture where the whole thing was the same shading, that's a good picture. You can do that. Okay. Now this top one, you've got the PZ orbitals that are just out of phase with each other. So if you had the carbon, oxygen, and you had 4 lobes for the PZ orbitals, and you had the shading where there was a node in the middle, and that's a good picture. So you're just bringing those PZ orbitals together, they're bumping into each other, but they're out of phase, and so there's no overlap. Notice what the highest occupied molecular orbital has. It's got a huge amount of electron density next to the carbon. That huge lobe, those electrons on that carbon in the highest occupied molecular orbital are going to be the thing that interact with other species. And so if we zoom in on this, this is really important for inorganic chemistry. So we can take a metal and we can put it in solution. We can put carbon monoxide in that solution, and it will snap onto that metal. Because of those electrons on that carbon, that lone pair, non-bonded pair will come up and associate with that positive cation, and it will surround that metal. And so then you have a metal that's surrounded by carbonyls, a very organic-y type thing. And so this sigma donation, look at the LUMO. The LUMO has a pi cloud that looks a lot like a DXY, DXZ, or DYZ orbital. And so it's very important in inorganic chemistry to have this sigma donation and pi back donation. And it forms a really strong, almost like a double bond between carbon monoxide and metals with their d orbitals. And so this is from our inorganic text, Cotton and Wilkinson, where you see up here that it's shown just with that electron density on the carbon coming in and associating with the metal and forming this sigma arrangement. And then the metals, d orbitals, d, x, z, say, comes along and interacts with the LUMO on the carbon monoxide and forms this pi type interaction. And that forms a really tight association between carbon monoxide and metals that have d orbitals. So again, that's a little bit of foreshadowing. When you take advanced inorganic, you're going to be talking about this quite a bit. Now we'll end with ethene. This is the most complicated one we'll do. Okay. Remember in grad school I did naphthalene, all the molecular orbitals of naphthalene. It was a beast. Okay. So we'll just look at ethene. We have the 2p, the 2ps, 2px, y, and z, and the carbons, but at least the hydrogens don't have any p orbitals. Okay. And so what we have here is really 3 MO diagrams. We have symmetry adapted linear combinations of the hydrogens over here. And when I say symmetry adapted linear combinations, I look at the 4 hydrogen atoms and I think, what are the possible ways we can mix these together? And that's what our next lecture is going to be on. It's going to be called the projection operator. So we take the character table and we use that kind of like a filter or a lens, and we project the molecular orbitals or the atomic orbitals through that lens of the character table, and on the other side we get an image of all the different symmetries that we can get out. So we run these orbitals through the character table, and on the other side we get symmetry adapted linear combinations of the orbitals. When I say linear combinations, it's that, you know, the 1s on atom A plus the 1s on atom B plus 1s on atom C plus 1s on atom D. And then you have all the different minuses. Plus this, minus that, plus this, minus that. So those are linear combinations. You're just making combinations of the different orbitals, and they all have different symmetries. So over here we'll have the hydrogen linear combination, and on the left we have the carbon linear combination. So it looks a lot like a C2 molecule. We've put the two carbons in the middle and we've made essentially a diatomic. So the ethene is like a carbon-carbon diatomic in the middle with 4 hydrogens stuck around it. Think about the molecule. A double bonded carbon, diatomic in the middle, and then 4 hydrogens stuck on it. And that's how you make the ethene molecule. And in the middle we have all the molecular orbitals for those, and we have the symmetries of everything in this. This chart is in the computer lab up on 321. And so if you're ever up there, I'd encourage you to go look at it and see if you can understand it. I'm not going to ask you to build this chart. We wouldn't have time in a 50-minute exam. Okay, it'd be awesome. But I would like for you to look at it and understand it. So go by 321 and see if you can stretch what you've learned so far into a larger molecule. Just look at it. I've got the character tables in here and everything. It's 3 foot by 4 feet, so you can really see. And then it's also a PDF on Blackboard you can download, and you can zoom in and see all of the different pieces. Okay. And so these are combinations in the middle of the SALC AO, so that symmetry adapted linear combination molecular orbitals, to produce the molecular orbitals for ethene. And then you can zoom in on this area where the bonding orbitals are. You've got that little rainbow arrow. That's the full visible spectrum, so that's the energy difference in the visible region. And notice the LUMO is above that, and so the HOMO-LUMO gap is in the UV region, so that we could even predict from this that it would be a colorless compound. It would not absorb in the visible region. And then you look at that, it produces 6 types of bonds. And so then we go to the literature and look to see what the UVPS shows. And it shows 6 bonds plus the 1s on the carbons. And so once again, even in a larger molecule, not just a diatomic, the UV photoelectron spectroscopy favors the molecular orbital arrangement. Because if you had local bond theory, you would just have 3 peaks. You'd have the CC single bond, the CC double bond, and then the CH bonds. Now for water, why isn't water linear? I mean, you could make linear water. But as you start to look at overlaps of these orbitals, you end up lowering the energy enough when you go over to the bent form of water, and you can see that. But what's the bond order on this? I mean, this is where we get frustrated, because bond order really only works for diatomics. And so we don't really get into bond order when we get to polyatomics. So even though you're really learning bond order and it's useful to think about for diatomic molecular orbital diagrams, just beware that you really can't calculate the bond order for water. You just then have to look at the orbitals and see if there's nodes that break this particular bond and nodes that break that particular bond. You can look at ethene, and you can find orbitals that are bonding for carbon and not for the CH. So let's look at some of these. Is this orbital here a sigma or sigma star? That was really quick. Okay. Why do you think sigma star? The node breaks a bond. Which bond does it break? Breaks the carbon-carbon bond. But what about the CH bonds? So if I'm a CH bond, it's a sigma. Whoa, yeah. Because it doesn't have a node that breaks the carbon-hydrogen bond, but it does have a node that breaks the carbon-carbon bond. So do you see what I'm saying? That sigma and sigma star and pi star are really just useful for diatomics. You get to polyatomics, you just need to look at the orbital and see which bond it supports. This orbital supports the CH bonds and does not support the CC bond.
Is that why none of the sigmas have stars on them? Or
Yeah, and so when I talk about sigmas in this case for the polyatomics, I'm looking at the sigma framework of the molecule, and I don't have any stars on there because which one is it antibonding for? You know, I can't decide whether it's sigma star. I would have to say sigma star for the carbon-carbon, sigma for the CH, and it starts to get cumbersome. But I can say that there's no nodes that are in the okay, think about this. Remember, a pi bond is side-on interaction, and a sigma bond is interaction like between the atoms. And so notice that these here, like this one in particular, the electron cloud completely surrounds that carbon-hydrogen interaction. It's not above and below it, it's surrounding it. But look up here at the pi interaction. So this one is clearly labeled pi, and it's above and below the carbon-carbon bond. So that one is truly a pi bond because the bond is actually sitting on the node. And you have electron density above and below the plane of that bond. So you can say sigma and pi interaction, but as far as putting it in a neat box that says this is a sigma and that's a sigma star, and this is, the pi's are a lot easier to figure out in big molecules, but the sigmas, no, they're all sigmas for something. They're sigmas for, this is a sigma bond for all 5 bonds. All 5 bonds are supported by that molecular orbital. Okay, and here 4 of the bonds are supported by this one. Here, all 5 are supported by this one. So the CH bonds are supported because there's no nodes that break those CH bonds. The CC bond is supported because there's not a node that breaks that. And so those are, again, very, very nice. This one is supportive of the CH bonds, and this one's supportive of the CH bonds, but it's not supporting the carbon-carbon bond. This one is supporting the carbon-carbon bond. So you should go through it and look at those and say, oh, wow, this one supports this bond and doesn't support that bond. You should be able to look at that, and it's wherever there's a node. If a node breaks the bond, if it cuts between the 2 atoms, then it's not supporting that bond. Anything else? Okay, that's a good place to stop. Next time we'll probably have internet access and we can do a Kahoot.